Alrighty, guys. Today we are discussing the pendulum. The pendulum. Have you guys ever heard of pendulums, I'm assuming?
I have.
Yeah, good. They swing, right? Okay. So, when you think about a pendulum, what do you think of? Like, what kind of object?
Trying.
Is it ghosts?
A grandfather clock.
Okay, Trucks, what do you think of?
Like your grandfather clock?
Oh yeah, grandfather clock. What else?
Those little ball things.
Oh, like on like with the piano, like the.
Wait, isn't it the balls?
A time signature thingy.
What about like getting hypnotized?
Yeah.
What do they usually use in the movies and stuff? Yeah, like a pocket watch. Okay. For all of my examples today, I'm going to be using my lanyard because this is the closest thing that I have. Okay. But we're going to be talking about pendulums, and specifically, we are going to be talking about simple pendulums. Simple, yeah. So a simple pendulum is basically comprised of two things, a mass and a string, all right? So we've got a mass, and the mass is attached to a string. There's something important about the string, though. It's an adjective for it. Mass attached to a something kind of string. You have any guesses? No?
Massless string. Massless string.
Okay, the reason that we consider the string massless and that we like to mention that is because if we didn't, then we'd have to take into account the mass of the string while we're doing the physics, and then it gets messy, and we don't want to deal with that, okay? We don't want to deal with that. So our string is going to be considered massless, okay? Now, what variable do you think we use to represent mass? M, yeah, and what are the units? Kilograms. Okay, what unit, well, let me think here. So string is going to have a value too. The value of the string is going to be the length of the string. What variable do you think we would use to represent the length of the string?
L.
Yep. What do you think its units are?
Kilograms.
Meters. Meters. So we're still using kilograms and meters. Does the string have a mass? No. Okay. So one more note on the mass. Sometimes it'll get called something else in physics. It'll get called a bob. A bob.
Like bob.
Like it's called bob. Like you know, like when you go fishing, there's like bobbers.
Yeah. Oh, bob. Yeah.
Sort of like that. So they call it a bob. Yeah, it's all the same. But sometimes instead of saying you've got a mass of however many kilograms, they're going to say your bob is this many kilograms, or you've got a bob at the end. Okay. So why we're talking about pendulums right now is because they move in simple harmonic motion. Okay, so they move in simple harmonic motion. There is like a little like caveat, I guess you could say, to this. It only moves in simple harmonic motion when we have a small theta. Okay? Small theta. Now what that means is, let's say this is our pendulum, right? When I move it a little bit off to the side and create a small angle, it's going to move in simple harmonic motion. But once I surpass a certain angle, is that really simple harmonic motion anymore? No, it's a little messy, right? So this is only going to be true for small angles. So let's talk about and look at where this angle comes from, what it represents, everything. We're going to draw basically a situation of a simple pendulum, okay? So right down the middle, if it were dangling, it would be considered to be in equilibrium, right? Okay, but do pendulums always just stay in the middle? No, they swing off to the side, right? So So here's our mass. Here's our pendulum. Okay, so this string is represented by an L for the length. Our bob is an M, and our theta is right here. Okay, that's our theta. So it's from the equilibrium over to wherever we have swung. All right? This right here is our vertical rise from equilibrium. So like this is where our bob would have been in equilibrium. It has rised this much by swinging up. Sort of give you guys a visual of how that happens. Is like, let's say that it starts out here. You see how when it swings up? Mm-hmm. Okay, so there has been a slight vertical rise from equilibrium whenever we go on the pendulum. The last part that I want to label right now is this. This would be considered the path of the pendulum. Yes, Trunks?
Like with using your lander and stuff, isn't it like not a true simple?
It's not.
Just because it's not in the back, right?
Yeah, it's not a true simple pendulum, but it works for examples for visuals. Yeah, because my string is definitely not massless. Okay, do you guys have all those labels down? Okay, so I'm going to erase the labels, and we're going to put up some new labels. Basically, we're going to do the free body diagram of the bob. Okay?
Probably, yeah.
I mean, if you want to label it all in the same place, you can. That's up to you, but I'm not going to because I want it to be cleaner for you guys. Okay, so free body diagram of the bob. What force is that? What kind of force is that? Tension. It's a tension force, okay? Because it's a string, right? It's a tension force, all right? What kind of force is that?
Gravity.
Mm-hmm. And what's the force of gravity equal to? What times what?
Mass times acceleration.
Mass times that acceleration due to gravity. Awesome. Okay, now when we do these pendulum problems, we're going to do something that we did previously. We're going to tilt the axis, okay? And when we tilt the axis in pendulum problems, at least my preferred method, is that we make the x direction in line with our tension. Okay? So this is our x, and this is our y. So tension is completely in the x coordinate, right? Okay. What about gravity? The force due to gravity, is that all in one direction? No, we've got two, okay? So we have the force of gravity in the x direction, and we have the force of gravity in the y direction. This is when theta comes into play, okay? The x component of gravity is going to be mg cosine theta, and the y component is going to be mg sine theta. So you guys get to keep with that nice little thing where x is cosine and y is sine. And that's one of the reasons I like to tilt my axis like this, okay? I have a question for you guys, though. Since this is simple harmonic motion, one of these forces represents a new force we just learned about. It starts with an R. What was it? Huh? No, we haven't talked about radians. We just learned it, you guys. We are definitely not talking about rotation. Restoring force. Yes, you guys, we just learned about the restoring force. Which one of these do you think is the restoring force?
Gravity.
What part of gravity?
The Y.
The Y. This right here. How do we know that this is our restoring force? Because it's pointing towards equilibrium. Okay? So it's the restoring force. Now, somebody in third period asked me a pretty good question. They were like, well, okay, that's all fine and dandy for when our pendulum's gone to the right, but what about when it goes to the left? You know what's going to happen then? It basically gets mirrored, you guys, okay? So, we still have our force due to gravity. We still have our tension. And then the x is still the mg cosine theta. And our restoring force pointing towards equilibrium is still mg sine theta.
Oh.
So your restoring force stays the same. It doesn't magically become mg cosine theta. It's going to stay mg sine theta. Now it's just pointing in a different direction. Will it have two different aspects of gravity when we're at equilibrium? Are you sure? Because it'll just be pointing straight up and down in equilibrium.
I found this on the web.
But it would have changed the mass would have changed.
Huh?
But the mass would have changed the.
No. So like what I'm saying is when we are at equilibrium, let's think about this, you guys.
Mhm.
When we are right here, look, all we have now is the force of gravity and the force of tension. And they're both in which direction, X or Y? Y. Or you could consider the axis still flipped. You could say they're an X. But either way, they're both together, right? They're not broken up into components when they're there. So when you're straight down in equilibrium, you just have the force of gravity. You don't have it broken up into components. So that's just something to think about, keep in mind. Alrighty. So you might be wondering, well, how do we find the period of a pendulum?
Yeah.
Because the other one we learned, right, it was that period is equal to 2 pi times the square root of m over k. What's k stand for? Do we have a spring constant here? No. Okay. So our equation for the period of a pendulum is that t equals 2 pi square root of L over G. Okay? So our period is equal to 2 pi square root of L over G. L standing for the length of the pendulum, and G standing for acceleration due to gravity. So, what is G on Earth?
9.8.
Is it going to be 9.8 on Mars?
No.
No. Is it going to be 9.8 on Venus?
No.
Is it going to be 9.8 on the Ferengi homeworld?
No what?
You guys don't watch Star Trek?
No.
What?
The TV show, like the old one.
Gravity just points down.
I never watched like movies. Just the show.
I don't watch
There's
that.
more than one show. There's the original series, there's Deep Space Nine, there's Next Generation, there's Voyager,
I
there's...
think that's the original. It's like the whole.
A nerd. Man, y'all don't give her like that.
You guys, listen. If you haven't seen all the Star Treks, you're obviously using Netflix wrong. The only good thing on Netflix is Star
you're
Trek.
using Netflix, right?
No, I
I only use
See, my family, my dad always respected Star Wars and Star Trek because they're very different ideas. They have very different messages that they're trying to get across to their audience.
Oh, they're both
Huh? It's okay. It's nothing like Star Trek, though.
watched the Star Trek original in 1960.
Okay. You guys are obviously uncultured, so we're going to move on. Now, let's see here, though. You guys have at least used a yo-yo, right?
Yes.
Okay. So, in this next example, we're going to talk about a yo-yo. Did you guys know about the yo-yoing competitions that happen? Like, it's a legitimate thing. Like, people compete to be the best yo-yoer in, like, the world. It's crazy, okay? So, let's say we have a yo-yo, all right, you guys? And our yo-yo has a string of length 0.75 meters.
So this is an example.
This is an example, yes. It also tells Anderson to pull his mask up.
Whoa. I've never heard of yo-yo doing that before.
Well, it told you right now, pull it up. All righty. And we want to know, what is the period of oscillation if the yo-yo is allowed to swing back and forth at the end of its string? You guys, where do the yo-yo competitions take place? What planet? Earth. So what's our G?
9.8.
9.8. Awesome. So with that information, can you guys solve for the period?
Yes.
Do it. Let me know what you get.
I got 1.
Oh, hold up. Other people have not had time to even type that in yet. Give them a second.
I got time. I talk slow.
Yeah, but you move ahead faster.
Yeah, you do. You're too small.
You get excited. You don't need to apologize. I want to make sure at least one other person has it, though.
I got it.
Okay, cool. Well, listen, Nyla got there first. She was excited. We're going to let Nyla tell us what her answer is.
I got 1.74. I agree.
For gravity, would it be negative?
I thought you
Or
No, you don't have to do negative.
I
It's
agree
what,
with
hun?
Nyla. 1.74. I got the back.
Yeah, because, Trunks, think about it. If you put this as negative, you're going to get an imaginary number.
Yeah,
I
look
just
at
did
the
that
main error.
afterwards to prove that as a negative.
No, because time is also not negative. All right. Good job, you guys. Good job. What about if we decreased the length of this string? Let's say now it's only like 0.25 meters long. What's going to happen to the period? It's going to shrink. Yeah. How do you know it's going to shrink? Because it's on top, right? It's up here. It's going to take less time, okay? So, think about it. Watch this. Okay, so here's a period. And it's a decent one, right? But then what if I take it down here? It's going faster now, right? Yeah. Okay. Cool. Awesome. Now, what about if we increase the mass of the bob? What's going to happen then? We increase the mass of the yo-yo. Yo-yo weighs more now, you guys. Are you sure? Do you see mass anywhere in this equation? Mass does not affect a pendulum. It does not affect the period at all. Mass matters none. So if you're doing a pendulum problem and they mention the mass, do you care? No, you're like, that's really cool information, but no, I'm not interested, okay? You're not interested in the mass. So a grandfather clock was mentioned when I asked for examples of a pendulum. So let's talk about a grandfather clock, okay? We've got a grandfather clock, and it takes 1 second to get to a side. So this is a second. We got another second. So to go back and forth, how many seconds would that be? To get from here to here is a second, and then to get back is a second. 2 seconds. Okay, so what's the period of that grandfather clock? 2 seconds, right? Okay, so the period of our... So disrespectful, Belle. Okay, so the period of our grandfather clock is 2 seconds. Now, this grandfather clock is on Earth, and I want to know. Give me the length.
Okay, we gotta rearrange.
So now we've got period is equal to 2 pi square root of L over G, and we want L. We want the length. How are we going to find that, you guys?
First we divide by 2 pi.
Good. First we divide by 2 pi, then what do we do?
Square root.
And then you multiply G.
Does everybody realize what we just did? Do you guys know? Did you see everything happen in your heads?
Yeah.
I see some confused eyes, so I'm going to show it anyways, okay? We divided by 2 pi and got square root of L over G. Then we squared both sides to get rid of the square root. And then you're left with L over G, so you bring the G on over, and you get T divided by 2 pi squared times G is equal to L. And what you guys should be doing now is busily typing away on your calculators to tell me what is L. Yeah, but okay, what'd you say the units are?
0.99.
0.99 meters. Yes, Trunks.
What happens if it would be like in deep space and there's like no gravity being applied?
There is gravity everywhere. There is no such thing as no gravity. No matter how deep you are in space, there is some gravitational constant. So you would need to figure out what that is. So like maybe you'd be given the length and you'd be asked to solve for G. Right. Or you would have to be given G to solve for length. I'm not going to just shove you out in space with a pendulum and then no way to measure the length or no definition on what the gravity is out there. You'd get one or the other from me. But yeah, you guys, very important. I know you're taught to think that in space there is no gravity. That is a lie. It's a big fat lie. There is still some semblance of gravity in space. Nyla, what's up? You have a question, hon?
Yeah, I have a question. So, if you wanted to find we just found link, right? You wanted to find, we already have gravity.
Huh?
We're not gravity, we already have that. Never mind.
Never mind?
Because you know how, like, you couldn't have, like, another equation we had in the past, you couldn't have to move over the one place, like, you know, like, that to, like, move the top one.
That's how you get G. So, we're going to tie this back to some prior knowledge, okay, you guys? Let's say we've got a pendulum and it's constructed from a string, and the string has a length of 0.627 meters. And the mass of the bob attached to it is 0.250 kilograms. When set in motion at a certain location, it completes one oscillation every 1.59 seconds. And we want to know if the pendulum's held at rest in the vertical position and the string is cut, how long does it take for it to travel a distance of 1 meter? So we're looking for time to fall 1 meter, which means that it would be like displacement would be like -1 meters. And it's like this pendulum right here. It's just chilling. It's just chilling at equilibrium. It's just hanging out right there.
So we're trying to
This is 100% prior knowledge. This is not an equation you learned today.
Is it the sine one?
We don't have to use an angle at all. This thing is just straight down.
Hold up. What was the question again?
We want to find out how much time after we cut this thing it takes for it to fall a meter.
Oh, free fall. Right.
Okay, what kind of equations did we use with free fall? Start with a K.
Kinematics.
Kinematics. Woo! Okay. So, kinematics. We learned that the change in position is equal to the initial velocity times the time plus 1/2 acceleration time squared. Okay, if we are chilling at equilibrium and we're at rest, what up here can be 0?
The V not T.
So we're left with delta y equals 1/2 AT squared. How do we get T alone? Okay, we multiplied by 2, then what do I do? Divide by A, okay, then what do I do? Okay, so delta y is -1. What's our acceleration? -9.8. So you're going to do 2, well, the square root of 2 times 1 times -9.8. That's going to give us how long it takes for it to drop. Let me know when you got your answer.
I can't even find what I'm supposed to be doing right now.
Do you guys agree with Trunks?
What did we get?
0.45?
Yeah.
Yeah? Awesome. Okay. So, can I erase this? Go on to another example? I'll give it a second.
Since we have a second.
No.
No, Anderson, we're not doing this. We've got like one example left, and then we're going to talk about something.
Okay. That means Anderson, let's not make it.
We're not talking about space again?
Anderson, we've already told you why there is semblance of gravity in space. We've already gone through this.
Now, imagine this, right? So, in space, there's nothing around you.
Yeah, I didn't know that.
Like, it's just deep space. Like,
Okay,
nothing.
Anderson, there's
And then
a
there's no
star
gravity.
area.
Because you're
Even if the
floating.
gravity
Right?
is 0.000.
Just because you're floating. Okay, so listen. Hold on. You've seen the footage of people on Mars, right?
No.
You've never seen footage of people on Mars.
There's nobody on Mars.
Well, on the moon. Sorry, the moon. You've seen footage of people on the moon at least.
Yeah.
Okay, because on Mars we've at least had like little drones go up there. Okay, think about it. When people are on the moon,
They don't float. They hop.
they are floating for the moment when they are in the air due to the hop. What brings them back down, Anderson?
That's not a float. That's just a long jump. There's a difference. That's not a float. It's just a long jump.
He's
Don't
just
you-
trying to get on your nerves. Don't you?
Oh, Anderson always gets on my nerves. He knows that.
Yeah.
I can't stand him.
But
Trunks, what's up?
I think it's Anderson saying that in the theoretical scenario, if there was nothing.
Oh no, he's not talking theoretical, hon.
No.
He's not talking theoretical. He's just trying to be annoying and to postpone the lecture for some unknown reason, because I'm sure you would all like to be done.
Yes. I'm not. I'm genuinely confused. Because I can understand the moon because it's big.
If you don't understand, ask her after class. I'm trying to play cards.
He gets a whole lot on his opposites and stuff.
Wait, please.
But somehow.
Anderson, listen, hun, shut up, shush. I'm done, man. I'm done. If you want more information on this and what we have given you is not enough, you're going to go home and do your own research and you're going to be quiet for the rest of my class. Do you understand? Okay, thank you. All right. What is the frequency of a pendulum of length 1.25 meters where G, you guys were getting intense, instead of being 9.8, it's 9.82?
Oh, I'm scared.
Give me the period.
Hold up, I gotta. Give me a second. C equals 2. I got this. Do I have any over G? Go. Where's my timer?
Wait,
Is that point?
are we looking for frequency or?
You're looking for a period.
Okay. Sorry, at first I thought you said frequency. Sorry.
Where would you?
Well, I mean, technically, you could also find frequency.
I got 2. Sorry.
2 point what?
2.4
What are the units?
seconds.
Seconds. And since Trunks mentioned it, find frequency.
Hold on. Wait, no. Oh, I think I did. Okay. How you fucking receive it? Girl, you asking the wrong one. You said you got it. I think I did. Is it point?
Isn't it 1 divided by?
It's going to be 1 divided by the period.
Yeah, I got it. It's
Oh, yeah.
0.45.
You guys got 0.45?
Yes.
Woo.
Yeah. I kind of guessed with that.
Okay. What are the pendulums on your body?
What do you mean?
What part of your bodies are pendulums?
My arm.
Your arms and
Legs.
your legs. So you have pendulums on your body. Just keep that in mind. That's fun. Now, something that I just want to touch on that we'll talk about in much more detail later on is the idea of this thing called resonance. Okay? Okay, so you've heard of resonance. What do you think of when you hear resonance?
I think of disappearing. Like, disappear. Yeah, like resonance. Like, disappear.
You think of Renaissance. You think of disappearing. Trunks thinks of
Like an alien movie?
an alien movie. Anderson thinks of something related to gravity, I'm sure. What do you think of Anderson?
What does resonance mean?
Ah, okay.
She thinks healthcare.
That's a genuine question.
No, it is. We're about to talk about resonance. I'm trying to see what you guys think first, though.
She thinks healthcare.
I think of like God.
You think of God?
Yeah, because he resonates.
Oh, that's good.
Well, I get that. Okay.
Okay. Lexi?
That's right.
Resonance is when something settles.
Settles?
Is it a resonance? No, that's residence.
Yeah, that's residence.
Just something like left behind.
Wow, that was
I think it means disappearing.
Okay. So, you guys, resonance has to do with frequency, okay? Everything in the world has some natural like frequency at which it operates at, okay?
Right.
And resonance occurs when your natural frequency is met. And I do have a visual of that for you, Anderson, that we're going to watch, okay? There's a visual I'm going to put on the board, okay?
Okay.
So, occurs at natural frequency. Do you think this causes a big amplitude or a small amplitude?
Small.
Small.
Big.
Medium.
Large.
Large.
Very large.
Okay, never mind.
Large. Huge.
They're not.
Large amplitude. It causes a huge amplitude.
How big?
How big? I'm going to show you how big.
Ooh.
Have you guys ever heard of the Tacoma Bridge incident?
No.
No, that's
Oh, I
okay.
probably have. Oh, wait. Was it about like a bridge like swaying back and forth because it collapsed and there was a dog on it and it died? And yes, I got you. I watched that last
Look
week.
like the dog on the bridge.
I watched it like
The dog did not die. The dog got off. Somebody ran on and saved the dog. Okay, so you guys, it was like 5 words.
I like that.
Wait, what was after large?
Amplitude.
Large.
Yeah, you're gonna see it. It's crazy.
I know.
And it's because there are winds that come through that match the frequency. Huh? Yes, you're done with notes.
Okay.
This happened a long time ago?
Not like a long time ago, but a half a time ago.
The 19th century.
All right, you guys, you ready for this? It has a great soundtrack. Yeah. Okay, so it sort of starts out as just these little sways. And you guys, this is like metal, concrete, asphalt bridge.
You won't catch me on that.
Yeah, so that's how it starts out. You guys, it gets worse. No, it's just winds.
When? Oh, you won't catch me on that.
Hold on. I'm trying to get a better view of it. So this is like the view if you were looking down the bridge. Do you see how it's going? Okay, so this is them going on to get and rescue the dog, you guys, okay? A professor goes on, he rescues the dog, and he brings it back. You see how it's gotten worse? He's in this car back here. So you're going to see the professor coming up with the dog. I'm going to make sure that you see that the dog makes it okay, all right? I know exactly what she's talking to. So here's the professor coming up with the dog.
He's trying.
Did you not save the dog? Which save
What if it gets like too strong? You stand on one side and then one side.
People say it's
And he does. They said he risked his life to save the dog. The dog was at the bottom on its leash. Okay, you see the car?
yeah.
Why does he just like stop your car? He was already there. That's what I'm telling you. You do not see.
And then
Guys!
Nobody died. Like the fish looking up.
Like, what in the world they doing over there? They're partying on that.
and you see how the stuff that's left, it's still going.
I'm sorry, you would never catch me on a bridge like that.
So like another classic example of resonance that you guys might be familiar with is, have you guys ever seen the thing where like the opera lady sings and breaks the glass? So what happens when she breaks the glass is that the tone of her voice is matching the frequency of the glass. And it breaks it, it shatters it. But yeah, see, everything that's left is still going. It's just like,
Who was that in?
that bridge is done.
Or is it come on here?
Did it just shake?
It was winds. So the winds that came in were matching the frequency. And after this happened, you guys, engineers had to start getting a lot more thoughtful about how they were building things because this was an engineering error. Because the drawback of engineers is that they're not physicists. So they don't really think about everything. Sure, they have to take some physics classes, but they're not physicists.
Yeah, they
Okay?
had.
So engineers had to start thinking things through a little bit better after this happened. 'Cause